Thank you for having me here today, Chris and Ben. I'm going to talk to you guys a little bit about some approaches that we found that can make your teaching of cement hydration a little bit more effective for undergraduate classes. And before I start, I'd like to acknowledge my fellow co-authors, Ken Hover, Anton Schindler, and Alexandra Radolinska, who it's been an absolute joy to work on this with. So one of the struggles or challenges maybe of teaching about hydration is that compared to many of our other civil engineering courses, it tends to be quite a bit more qualitative in nature. So we're teaching about theory and qualitative ideas rather than employing equations and mathematical expressions, which at least in my course, it's one of the first courses in our civil engineering major. So students are right out of higher level math, calculus, physics classes where they've been doing lots and lots of problem sets and employing math equations, et cetera. And now they're going into something completely different. And so we have 4 different areas in which we have some recommendations to make as far as how you can supplement your lecture material to increase student learning. So the first is through use of demos and metaphors within your class. The goal of this is to link these hydration processes, which are very new for many students, to systems that they may already be familiar with. So we're trying to build off of something rather than starting from zero, give ourselves a little bit of a head start. In addition, we want to incorporate experimental activities whenever possible. We might take it for granted, having been in this industry for a while, that many students may never have seen cement or aggregate in person before in their life. So we want to allow students to interact with those materials, to get their hands on them if possible, and even just to compare things like the particle size of cement versus sand or coarse aggregate. We also want to implement some alternative approaches to assessments and homeworks in our class to make sure that the students are quickly and consistently and regularly interacting with the material that we're teaching in class. One thing I noticed in my first semester teaching was that if I didn't force them to engage through homework and graded activities, many students waited until about 2 days before the test to try and cram all of the material, and they don't realize how much they're actually being asked to learn in terms of terminology and theory and application, use of these materials, interactions between things, effects of different components. It's a lot, and students don't really realize that until they sit down 2 days before the test to study. So if we can get them to engage on a more regular basis, they will be ahead when it comes to overall learning. And then finally, we want to make sure with these sorts of theoretical concepts to make sure that the students are applying what they've learned to how they're going to use this in the real world, noticing real world applications of really theoretical concepts like hydration. I do want to point out too, just like Matthew was talking about, we have a paper that's going to be published on this, and we're discussing all of these approaches in much more detail in the paper. So I encourage you to check that out for more details. Okay, so my first approach to working in extra ideas and building off of concepts within a hydration class is to use metaphors, specifically food, is really effective for teaching about cement components and cement hydration processes. We can use things like coffee, which many students are very familiar with coffee. They're exploring espresso and grinding and brewing their own coffee in their dorm rooms. And so we can liken cement hydration rates and the influence of fineness to the difference between that espresso and the drip coffee. We get more flavor faster from espresso. With type 3 cement, we get more reaction faster, the same sort of relationship. We can also liken our hydrated components to foods. I like to talk about CSH being like the pot of spaghetti noodles that you drained and then forgot about and left in the pot. And so we have these backbones of calcium silicate strands that are intermixed and harden over time. And then they form a solid, hard, strong microstructure that we can't break up and eat anymore, but it's still full of porosity. So this provides a really nice metaphor for our CSH that's really something that the students can visualize. We can compare similarly with the kitchen apparatus, plates of calcium hydroxide to plates in our cabinet, where they're going to be strong when they stack up on each other, but weak if we apply lateral loads, like an earthquake. Similarly, we can talk about workability in terms of butter and cookies. If you add too much butter, you're going to get a thin, crispy cookie where your chocolate chips have fallen to the bottom and burned on the plate. On the other hand, if we don't use enough butter, we won't be able to get that cookie to spread out and get it to the size and the consistency that we want. So all of these provide some convenient metaphors, and students are well aware of the foods that they eat, and so they can engage with those ideas of the foods and apply them real easily to our system. Plus, it's fun to talk about food in your class. So a second technique would be to employ demos in your class. Demos have been shown to increase overall learning gains compared to lecture-only formats. But I definitely want to caution you that preparation is key for these things. You don't want to just think up an idea and then bring it into class. You need to prepare your materials. You need to make sure that you know where your electrical sources are that you're going to need, know how to use the Elmo or the camera, and make sure that your demo is going to work out as planned. So you need to practice this beforehand, because it's also been shown in pedagogical literature that if you provide a bad demo, it can actually reduce learning compared to that lecture format. So you distract students, you get them to focus on the wrong things, or to think only about the problems that you had in your demo, not about the relationship between the demo and the material that you're trying to teach. In addition, we can't just do demos. We're not serving the students best if we are just being performers. We instead need to engage them in the process. They need to take part in that process. That could be having them help you perform the demo, but that's still only going to engage a few students. So we can also engage the students by allowing them to touch and play with the demo apparatus or the bags of material or whatever, by passing it around the classroom, or by having multiple sets of material and putting the students in groups. We can have the students predict the outcome of our demo through a poll and employ sort of a hypothesis scientific method sort of function. We can also guide them to developing a specific research question if we're looking at real specific topics with this demo, and then do an after action and see if that demo answered their question. We can also use demos to help clear up muddiest points in homework, or have them build off the demo in their homework to do maybe some calculations associated with the demo, or elaborate on what happened. Okay, so a couple demos that have been really successful in our class. Ken Hover is very famous for using these sort of plastic spiky balls to simulate the CSH hydration product. And these are also nice in class. You can wake up students if they're sleeping. You throw them out into the lecture room, and then they can play with them, they can touch them, they can kind of see what it looks like for a cement grain to hydrate and grow the CSH needles on its surface. We can also see how CSH compacts and joins together between different particles. You can do this both with these plastic toys, which you can purchase pretty cheaply on Amazon. I got a set this year that was about $10 for I think 100 of them, or you can build your own with these polystyrene balls. You can further build off of this model by using certain numbers of balls, certain volumes of balls within a confined space to simulate water to cement ratios and gel space to solid space ratios. So building off of that, we can also use some 2D models to simulate water to cement ratio. I think this is something that we tend to take for granted, being familiar with the idea of water to cement ratio and what it means and how it translates to strengths. But I found that many students have a difficult time visualizing what a water to cement ratio means, or even understanding the definition of it. And so if any of us are carrying around dollars and pennies anymore, we can use this to simulate these different systems. Here I've shown two different water to cement ratios. In this picture, the pennies represent the unhydrated cement grains. This is the solid material you start out with. The dollars represent the overall volume of the system. So that would be your cement plus your water. And we can see very easily the difference in porosity levels for these systems. Starting at lower water to cement ratio, we are starting out with a much more dense system, something that's going to require much less hydration in order to generate strength. And this can lead us into a discussion about Power's model relative to gel space ratio and its relationship to overall compressive strengths. So we can integrate the idea of strength development based on porosity with these little models of pennies and dollars. You can take this a little bit further by having students in their homework calculate the numbers of pennies that you would need for different water to cement ratios for different structures. For the water to cement ratio you would see in a pavement or a sidewalk or a UHPC, and kind of simulate that water to cement ratio setup. If you are able, I highly encourage you to use experiments in your class, even if it's just a lecture class. And so we've provided in the paper a couple examples of some easy experiments that you can use. Experiments are wonderful because they give students a chance to really see and feel out the materials. They get to touch it. They get to see what those particles look like. After some simple experiments, I often have students say that they really understand what we're talking about in class, even if we're just discussing pozzolanic reaction or what fly ash is. So having been able to use their other senses to feel out these materials helps students situate themselves a lot better. It also can allow students a chance to analyze the systems and apply theoretical ideas to real life concepts. And it can provide some space for some creativity, a little bit extra fun. So one way that you can easily do this in your class, even if you don't have a lab, is through use of these workability and hydration bags. So we simply form a couple bags with different amounts of cement. We mix the water in class, and then we can hand it around the class, let the students feel the difference in workability, thickness of the paste. If we start them before class, we can sometimes also feel the heat release, and we can compare that with something students, at least football students in northern climates, are really aware of, and that's the hot hand warmers. We can take this another step by tracking heat release in a very simple calorimeter system here. So we see we'll put our cement plus water system inside of water, and we can track the heat increase over time. We can compare that to similar amounts of the hot hands hand warmers, and students will be absolutely floored to find out that actually cement plus water will release more heat than our hot hands hand warmers. You can also, at the end of the class, if you don't track the heat, throw these out to students, and they're always happy to have a little bit of heat to walk home from class with. You can take the calorimeter idea one step further by implementing some low-tech calorimetry in your class. If you have a research version of this, you can definitely use that as well, but many times those are busy and filled with funded research, or maybe too complex for use with undergraduates. And so you can create your own through use of some coffee cans with some expandable foam that you situate a plastic cup in. You can then have students mix these mixes in class, put them in the cup, and we track temperature increases with the use of eye buttons or a thermocouple in a simple computer DAC system, or even a Raspberry Pi. This is nice because we can compare changes in hydration rates and total reactivity, heat release over time of different materials. And we can also use either common materials, as I've shown here. We were doing an experiment with different water to cement ratios, fly ash, class C and class F, silica fume, and admixtures. Or you can have students bring in things that they want to investigate. So they can bring in stuff from their kitchen. This semester, students brought in coffee. I've had baking soda brought in, wood fibers, lemon juice, all sorts of things. And then you can evaluate the effect of those materials on their system. This is a really nice way to link the hydration stages that we talk about very frequently in cement hydration lectures to how things react in the real world. You can see that our data isn't that great here, so you wouldn't want to use this for a research application, but for the purposes of a class, it works just fine. And the other thing is, in our paper, these can be rather complex to analyze. And I realize that, and not everyone may use these in their research. So in the paper, we've detailed some of the things that you want to look at, some of the analysis techniques that you can use to understand these systems a little bit better, so that you can create assignments for students to understand what they're doing. Right, so in addition to in-class techniques, we also want to think very carefully about how we are conducting assessments in a cement hydration class. There are some challenges associated with learning about hydration. First, the material is pretty qualitative in nature. We don't have a lot of quantification available other than these calorimetric techniques. We also cover a lot of fairly non-linear materials. So we're talking about things like the influence of temperature, the influence of curing, SCMs and pozzolanic reaction, sometimes shrinkage, and many other topics, which are all interlinked with the idea of hydration, but not necessarily building linearly. And so students can find themselves getting lost within the topic. They may also, coming out of physics and math classes, be unfamiliar with the techniques for learning qualitative material. And they may also prioritize classes that have earlier deadlines and more frequent assessments, more frequent homeworks, and put off their studying for a while. In addition, students may focus on anecdotal stories or the wrong concepts, things that are relatively minor impacts on hydration, instead of focusing on larger impacts like water to cement ratio, influence of temperature, things like that. So we need to think about some different ways to conduct assessments and homeworks to guide them to efficient study patterns. My first recommendation for that would be to use 1-minute papers. Matthew talked about these a little bit, but we basically just want to ask the students at the end of the lecture, what's the most important thing you learned today? Or what's the muddiest point? What did you least understand? We can have students engage with each other and collaborate with each other by answering those questions together. And it also alerts us as the professors and teachers to issues should they arise. So we can see if students are focusing on the wrong topics or if they misunderstood something that we taught or if we mistaught a topic. And we can quickly address that in subsequent lectures through use of this. In addition, so I mentioned that in my first semester teaching, I noticed the students would wait until the day or two before to start learning all of their work. I also got very little engagement in class with students with topics that did build on each other. They would just, I got that deer in the headlights look. And so my approach to remedying this in my class has been through the use of daily quizzes. In this, I essentially eliminated all of the homework from my course. This is the only homework. The students have 5 relatively simple questions paired with each lecture, and those are posted after the lecture, so they have to go back, read the questions, re-engage with the lecture material, and they can write down their answers. They are allowed to work together, they're allowed to use the book, and then at the beginning of the next class period, we have an open note, open book quiz over one of the questions from that 5-question set. I am not trying to trick students with this. I typically choose the most straightforward, easiest question to attempt to give them the points. I just want them to engage with the material. I don't want to really grade them on it at this point. And then, so you've used the easiest question for the quiz. You can use these harder questions at a later time on their tests, which helps. You can let the students know that I'm trying to direct your learning. I'm trying to get you to focus on these things, and it minimizes the surprise that students can have on exams because you're using questions that they've already engaged with. One comment that I get frequently about the use of daily quizzes is why do it so frequently every single class period? Why not back it off to once a week, once every couple lectures? And what the pedagogical literature has actually shown is that students' learning gains are increased through every class period activities. So if you do a once a week quiz, and I actually tried this last spring before the pandemic, engagement's going to drop. Students will only review their notes typically right before that quiz. So they're going to engage with the material on Sunday night for a Monday lecture, not on Tuesday for the Wednesday lecture. Whereas with a daily quiz, they're going to be reviewing every night or every other night the lecture material, keeping up and getting a lot of practice with that material beforehand. I also have found that the use of daily quizzes helps students to collaborate with each other and form study teams a little bit better. They want to check their answers and make sure that they get that quiz question right every day. And so they'll come in a little early and talk to each other or come and talk to you as the instructor. And it provides a conversation point as well. All right, and so finally, the last thing that we want to make sure we're doing with our hydration teaching is to link that theoretical concept with real world importance. We have several techniques through which we can do this. We can use mill sheets to kind of demonstrate the importance of the things we're teaching about, phase content, fineness of our cement, interlinked with property development, set time, and strength. We can also have them exposed to specifications through a scavenger hunt. It can be pretty boring to read a specification, but it's a little bit more pointed, a little bit more directed if we have them look for specific things that we're talking about in lecture. So maybe we're talking about use of SEMs, and we can compare that with the limits that DOTs put on specification on SEM use. We can have them find the curing requirements or the opening requirements calculated by maturity, etc. Speaking of maturity, in my opinion, it is the best way to link our theory of hydration with real world results. So we're going to we can build off the cumulative heat calculations we did with our calorimetry and equate that to strength development in our mixes. We can also then link this with the use of test methods, ASTMs, and maturity requirements within our specifications. So we're going to link concepts of temperature, hydration rate, cumulative heat generation, all to a more tangible concept of strength development. We also can then link these ideas about theoretical strength development to what's required in our construction and testing specifications. So in summary, we recommend you take a multi-pronged approach to teaching about hydration in your class. First, the metaphorical approach, linking new concepts with material that students are already familiar with. An experimental approach, giving students a chance to interact with the materials, play, and see how real systems react. A reflective approach, which pushes the students to engage more frequently and consistently with the material. And an extensive approach that applies our learning to real-world systems and to industry. Okay, so I'd like to acknowledge the help of Dr. Maria Younger, who is one of my wonderful teachers throughout time at the University of Texas at Austin. She's been a great mentor in this, and all of our past students, who I'm sure all the other teachers here would agree, teach us just as much every semester as we teach them. I do see that there's a question about textbooks for cement hydration, and that is one of the things that we've covered in the paper, is a list of the most common textbooks for cement hydration. The one that I would recommend is the Meta and Montero concrete book. I actually have that right here. I don't know if the screen will let me show it, but this guy is pretty helpful. Oh, the white on the top, yeah. So pretty helpful in teaching about cement hydration, and it's at sort of an in-between undergrad and grad level textbook, so you could use it both for undergrad and grad classes. Chris, or Ben, do I have time for any more questions, or did I talk too long?
Yeah, you're good. You got we got a couple minutes for a couple of questions. Any other questions for Lisa? We can't hear you. Lisa, I'll ask one. So you've tried a few things. Is there anything you wouldn't try again that you have tried?
No, I don't think so. I want to echo what Matthew was saying about not biting off more than you can chew. One of the semesters I tried a bunch of different active learning techniques. So we did gallery walks, we did a jigsaw experiment, we did some polls, and every time you introduce a new element into your class, you have to take enough time to teach how to do that activity. And so it can really consume a lot of the teaching time, and students are often confused the first time. So I would say pick one method and stick with it. And then some of these like demos and experiments and things, you can allow a little bit more time to anticipate those. But the other thing, and it's not as much to do with hydration, but in my class is an overall materials class. And so we do metals and wood and concrete as well. And we're doing some opportunities for the students to actually design the experiments. They do the entire process rather than following a recipe. And that has been really helpful. I think to the students, I get a lot of good feedback about that. They engage a lot more with both the testing and analysis process. But one key with that is that you want to make sure you have a baseline set of tests or requirements for those systems. I was having students submit mixed designs for like one cylinder this semester, which obviously isn't going to do a good experiment. So if you can have them, make sure they're running slump, make sure they're running air, doing a couple compressive strength and a tensile strength cylinder, or using your resistivity or other setups.
Good.
That can be really helpful.